Hello and welcome to CS142. This is week 1. These slides roughly follow the book Building Java Programs. They are produced by my dear friend of over 30 years, Amelia Gahn, another of MIT's finest. Amelia actually started the online programs at South Seattle College. Thank you very much, Amelia, for letting me use these slides. So we're going to start with this concept map. A lot of these first couple of slides, I'm going to assume you already know. If you don't, then please read in the book to understand all these terms. These are very important terms, but I'm just not going to take the time to go over it because I think most people already know them. Again, these are terms I think everyone should know. Computer software. Now our first real topic, binary numbers. Now, ironically, I'm going to tell you that you probably don't need to know binary numbers for CS142. For 143 and for future classes, you will. Every programmer does need to know binary. Just like in our decimal system where the first digit is 10 to the 0, the second digit is 10 to the 1, you've got hundreds and thousands. This is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. So if I have a 1000, I know that it's 8. And a much more useful skill than binary is actually hexadecimal. Hexadecimal is used in all of our debuggers. When it wants to show us a value, it's going to show it to us in hexadecimal. So that's a very useful skill. Also, if you're wondering why hexadecimal is useful, go watch the movie The Martian. It's a really good movie. Java programming language. This course is being taught in Java. Many of you are coming from either C or Python. Those are all roughly high-level programming languages. They can do similar things, but the main difference is that Java is a compiled language. But unlike C, which compiles it to assembly and then runs on a very specific target, Java compiles it into a bytecode, an intermediary form. This bytecode here is not only machine independent, so it can run on a Mac or Windows, but it's also completely platform independent, so it can run, if you tell it to draw a window, the bytecodes just records draw a window, and then the individual runtime environment, the JVM, will actually figure out how to draw a window on that particular environment. So that's different than C. So Java has several different aspects built into it. I can't tell you all the reasons why Java is successful, but certainly one of the big reasons is that there are a large number of pre-written libraries in Java, so it makes it very easy to program. Okay, we're going to talk a little bit about the programming environment. So you are going to be writing Java code. Here's a sample of Java code. And then that is just it's really just a text file called .java. There's nothing special about the file. It's just that they use the .java extension to identify it as Java. Then you're going to pass it to the compiler, which is javac.exe, and it's going to spit out a .class file, and that's the Java bytecodes. That can then be run on any type of environment using the java.exe. You're going to be installing the JDK, which has the Java runtime environment, and after you install the JDK, you should be able to use java.exe and javac.exe, but I'll leave that for another video. Now, in the old days, up until the mid-90s, we just had text files that we had editors for, and then we had command line compilers and linkers. And that's how we did everything. But around the mid-90s, then integrated development environments came into being. And that means that you get to do everything all together in one visual program. It's great. So it really hides the details of going from the text file to a compiled bytecode to running the program. So some of this you don't really need to worry about too much, but that's what's really going on. So here's a picture of Eclipse, the IDE that we use in our classes. Here you see this is the Java source code here, and then when you run it using this button here, it's going to be displayed here. This is the console window. So I'm going to make another video on how to install and run Eclipse. So we're going to take a look at the Java program. So in Java, everything is built around classes. Classes is really an object-oriented term, and we're not going to cover that until we get to chapter 8. But just remember that everything goes into a class, and that the name of your file, that your Java file, has to match that class. That's very important. Now this right here, you see all these things here, these are placeholders. This is not actual Java code. This is just where you would put your methods. Inside of a class, you have various different methods. And the one method that is always required is the main method. Those of you who come from the C programming language recognize main as being the procedure that is always kicked off when you run the program. So that's carried forward to Java. Now, there's several terms here, public, static, void, which you don't really understand and it's too complex to explain to you now. I need you to memorize this, though. I want you to be able to say in your sleep, public, static, void, main, string, open, close, square brackets, args, with all of this punctuation here. This is absolutely necessary, okay? You're going to be typing this every day. So memorize that as well as the one on the previous page, public, class, name, curly braces, okay? So inside the class, you have methods. The first method is the main method. And then inside the method, you have statements. So next we're going to take a look at the statements. So the compiler needs to understand where things start and where things stop. That's why there are curly braces. That comes from C. And that's why there are semicolons. That also comes from C. If you ever have the chance to take a compiler course, you will understand quickly why it is that these things are necessary. And you'll understand why it is that certain things have semicolons after them and certain things have curly braces. And you'll also understand why sometimes you don't actually need curly braces, even though everybody uses curly braces. But in the meantime, you just start memorizing that you're going to need curly braces around these methods, and you're going to need semicolons after every line. So the first statement that you're going to learn about in Java is the system.out.println or println statement. The book insists that the correct pronunciation is println, but since it is, after all, an abbreviation for print line, I'm going to try to say println, although I think they're already starting to brainwash me into saying println. So you can just have the open close parens, and that'll print a blank line, or you can enclose a quoted string like this. And later on, one of the beauties of Java and also Python is you can put all sorts of stuff inside this print statement. The book tells you about escape sequences, and in the problems, you're going to need to really understand these escape sequences. Tab and new line are pretty easy. They're completely different. The confusing thing, and the book maybe tries too hard to confuse you, is that if you want to put a quotation mark or a backslash in a statement that you print, you're going to need to put a backslash in front of it. So every time you want a backslash in the output, you need 2 backslashes in the input. I think, I'm not sure if there's an example of that, but there are several problems in the book about that. There's also, in addition to the print line, there's also just a print statement. That will not create a new line. So if you want to stick 2 lines together, you can just use print like that. Also, you can always use the \n escape character. It's kind of funny because nobody uses print line and console output really in professional programming, but at this stage of the game, it's like the only tool that you have. So you're gonna be spending a lot of time with print line. Okay, identifiers and keywords. We're starting to get into the meat. Ironically, there are no examples in the back of the book for chapter 1 that actually require you to use identifiers and keywords. It's only in chapter 2, but it's important to know. You can start your variable names with a letter, an underscore, or dollars. And nobody ever uses a dollar sign character. And then it can be followed by all sorts of things. What isn't mentioned here is that you cannot use anything that looks like math, because anything that looks like math in a variable name gets the compiler confused. It thinks, oh, there's two things here. So you can't put a plus, you cannot put a minus, you can put an underscore, which looks a lot like minus, and the book tries to fool you and does fool most people about that. So remember that when you're doing the problems in the back of the book. Dash is not an acceptable separator in the middle of a variable name. Variable names are all case sensitive, and the convention adopted by Java is that you begin all class names with an uppercase, that you separate each name with an uppercase, whereas method names begin with a lowercase. An industry moment is that at Microsoft, we for the longest time used what we affectionately called Hungarian to name our variable names. We called it Hungarian because Charles Simoni, who was a Hungarian, invented it. And variable names actually include a type in the variable name. So if you have an integer that means the length, you actually called it I-length. And I still use that, and I find it to be helpful on larger programs. There's a small set of keywords that you cannot use. Once you know Java, you will realize you can't create a variable name like if. So these are not typically mistakes that people make. Okay, comments. So comments is something that the book, and really no books, spend enough time on. What I'm going to tell you about comments is that the most important thing for comments, as far as I'm concerned, and as all professional programmers are concerned, is that we want a very nice header, method header, that explains exactly what your method is going to do, okay? I don't need a line by line, blow by blow, okay? If you're doing something really unusual, yes, I do want a few lines of comments explaining what it is you're doing. And, you know, for every group of lines, I'd like a comment to understand. But the number one most important thing is give me a method header that explains what this method is going to do. Java also includes what they call invariants, which is taken from another language called Clue. And invariants are a wonderful, wonderful thing. They're a little bit beyond the scope of this program. But if you become a better programmer, you really should be using some sort of invariants to, well, I won't get into it. It's too far beyond the scope of this for now. But method headers, remember that. And specifically, there are two types of comments. You can do the double slash for a single line comment, or you can do anything between the slash star and star slash. This can go over multiple lines. Java also has a feature called JavaDoc, where you put your comments in a very specific format for the headers, and then JavaDoc will actually strip out all these headers. And it's a great thing. Again, when you become a more advanced programmer, I would highly recommend you do that. Program errors. So there are three types of program errors: syntax, logic, and runtime. These days, syntax errors are largely caught by the integrated development environment. As you're typing in Eclipse, it'll catch things, most syntax errors, and put a little red X next to your line. I'm not going to go through all of these, but you will not be able to compile your program if you have a syntax error. And a syntax error simply means that you made a mistake in as far as the compiler is concerned. You've confused the compiler because you've forgotten a semicolon, which is probably the number one thing. You forgot the semicolon, or you forgot a brace, or you didn't close a quote, you didn't close a comment, something like that. A logic error means that you've done something that compiles fine, but it's not going to work right. For example, you had a for loop and it went one too many, or you called the wrong method or something. The book says that the term bug, it was attributed to Grace Hopper. I actually met Admiral Grace Hopper in Boston in front of the USS Constitution, which is I believe, the oldest warship in America. And she was a very, very wonderful lady who did a lot of things for computer science. The other thing that the book never mentions, no book mentions, which is a real travesty, is that professional programmers spend probably 50% of their time, maybe more if you look at the long-term life of a project, debugging programs. So it's really, really valuable and worth it to spend time making your programs easy to understand and easy to modify. Runtime errors. So if you succeed in not make any syntax errors and get it to compile and don't make any logic errors and it seems to work, you can still fall victim to a runtime error. So you have a loop that continues forever, you divide by 0. These are things that are very difficult or basically impossible to determine before you actually run the program. Okay, so again, how to fix errors in debugging. So for CS142, the main way that they teach debugging is to stick extra print line statements in. Again, no professional programmer does this. There are some equivalents, but really professional programmers use the features built into your IDEs to set what we call breakpoints and to step into and over and through code, and that's where you start to getting into actually needing to read hexadecimal. You can actually watch the variables as they go through. I would definitely recommend you learn how to do that. Any investment in print statements is going to be not a very good use of your time compared to this. All right, so this is really the meat of the problems that they have for this chapter. Understanding procedural decomposition. That just means you need to take a complex task and break it into a series of smaller tasks. If you get anything out of this chapter, this is what you should get out of this chapter. So it's a little bit hard to explain. The example the book gives that if you want to make a cake, you need to understand you're going to make the batter, you're going to bake it, you're going to make the frosting and frost the cake. Personally, I don't think that's a very good example, but if it works for you, great. But the point is, you need to take a problem, you need to break it into sub-problems, because in programming, it's all about that process. You figure out what the overall problem is, and you figure out, gee, what are some blocks that I can use to solve this problem? And then you work to solve each of those blocks. There's lots of advantages. I won't go through these all. Let's go to an example. So for example, suppose you're trying to generate this output here with these two blocks. So it's easy to figure out how to solve this. You're just going to have a bunch of print line statements, and here are those print line statements. But there's a lot of redundancy here. We're starting to talk about incremental improvements. So you're going to start with all these print line statements, and you're going to instead figure out, hey, I can create a draw box that I can call twice. It's going to print a box that's going to print another box. Let's go to the next page. So now we've got draw box here. We've got one draw box, another draw box. We needed a blank line, so we're going to have a blank print line right there. So this is what we call a static method call. And this is something that the problems for this chapter are going to be asking you to do. They're going to asking you to take a figure like this and then write the code for that, but to reduce the redundancy by creating a static method and calling those static methods from the main. So this is very important for this chapter. Another thing that they want to teach you in this chapter is flow of control in a program. So I hate these diagrams. As wonderful a job as Amelia has done here, it almost makes it look worse with all these arrows going everywhere. But they just want you to understand that the computer has an instruction pointer. Well, that's probably not easier. The computer is taking this one step at a time, right? It's going to be starting here. It's going to go execute this statement, draw box. Draw box draws the computer's attention over to here, where it's going to follow these lines here. And then it's going to come back, do the next statement here, system out print line. Then it's going to do draw box, which sends it over here, does the draw box, comes back over here, and then you're done. So that's flow of control. The programs at the back of the chapter 1 are going to be asking you to understand the flow of control. So they're going to be having some confusing examples like this. please promise me you will not write code like this unless you absolutely have to. So for example, here, main, which is where the code starts, is going to call foo, which is simple, and it's going to call bar, which is, oh, it's not so simple because it's calling baz, which goes down here. And please promise me you will never do this. You're going to don't create a static method to have one print line in it, because there's much more overhead in creating this method than just putting the print line here to begin with. So this is just for demonstration purposes. Don't think that this is how real programmers do stuff. So after it's done with this, then it's going to put out another print line. It's going to return back up here, and it's going to do another print line. So the book is going to try to confuse you. Don't be surprised. This is not how real programming is, but it's important just to make sure you understand. So the two most important things from this chapter are really, I'm going to go backwards in the slides here, are understanding how to do this type of problem where they give you an output that they want, and you have to create a series of print line statements that's going to generate that output, and then be able to generate, eliminate redundancy by creating a static method that takes repetitious statements and allows you, the main method, to call those. So in terms of actually getting stuff done, that's number one. Long term, I would say the most important thing to get out of this chapter is procedural decomposition. So unfortunately, it's this diagram here that I don't really like because of the example, but it's the idea that you taking a problem and then breaking it down to smaller problems. Okay, if you get this here, it will make the next future chapters much easier. And basically, all the way through the end of this course, you're going to be given a problem to solve, and you need to be able to break that problem down and write code for the smaller problems. That is really the key of programming entirely. Now, both of these two things, procedural composition and the iterative enhancements and this type of, I'm not sure what the name of it, but doing this type of thing, both of these are also featured in video tutorials produced by the authors of the book. And if you have a brand new book, you get the code out of the front of your book and you can log on and see those videos. If you have a used book that's already had the code used, you can go to that same website and pay $24 and get access to those videos. I'm not going to reproduce those videos because they do a very good job of them there. But if you have any confusion about how this works, I would recommend you either read the chapters very carefully or you can see the videos for those there. Okay, so that is chapter 1, and thank you very much. Do give me feedback about whether you find these lectures on the PowerPoints useful. Also, if you don't think there's something clear here, you can also go to the book publishers slides, which we have on our class website, and take a look there and see if you like those slides better, and give me feedback about whether you like Amelia's slides or the book's slides better. Thank you very much.